In this class, we will discuss about a problem on finding the effective section modulus of a given code form steel section and hence how to compute its load carrying capacity for a given span. Now, this is the data given. Young's modulus of steel 2 into 10 power 5 Newton per mm square, yield stress 280 Newton per mm square, odd dimensions, whatever is given in this sketch, it is in millimeters. The effective length of this span of the beam is 3 meters. It is simply supported, and the average stress you can take it as 85 MPa. Now the question is, what is the safe UDL it can carry? So this is the section given. So the dimensions are in millimeters. This is the flange. You can say 120 mm is the overall width. 90 mm is the depth of the web portion on both sides. 15 mm is the overall width of the lip portion. Now here, to find the safe UDL, first we need to calculate the section modulus. Of course, section modulus we have to calculate for the reduced or the effective section. Then we have to calculate the moment carrying capacity. Then since it is UDL, you have to equate that moment carrying capacity to the maximum bending moment, which is Ws square by 8, and then we have to find out W. So this is how the procedure runs. Now here, so these are the equations which we are going to use. Of course, when we are calculating the moment carrying capacity, we have to multiply the Zxr means that is the section modulus of the reduced or the effective cross section along the x direction, and Ft is the tensile stress that is going to develop. Normally, the tensile stress we can take it as 0.6 times the yield stress given, which is 0.6 into 280, which is 168 MPa. So after getting a Zxr, we can calculate M, and this M we have to equate it to W square by 8. So M is known, L is known, L is 3 meters, that is 6000 mm, which span of the beam. You can calculate the W, which is the UDL. So this W you are going to get in kilonewton per meter, or it is the same as Newton per mm. So kilonewton per meter and Newton per millimeter is the same. Now first we need to calculate Zxr. For that we have to calculate this very important limiting stress value, that is the maximum stress value that can develop in a stiffened element in the case of a code form steel section, which I have explained in the earlier video. So this is the equation which is given for finding the maximum stress. Of course here it depends on the W by T ratio also. Now here this is what I have to take now. This is the flange. So this is the stiffened element because on both the sides it is supported. Now W is nothing but your D here. So D, how to calculate D? For the flange, D is given by this overall width, that is 120. From that you have to deduct this what is that 3 mm, which is the radius. The radius of at this junction is 3 mm. So 2 times you have to take. So 3 into 2, and from that you have to deduct the thickness. So this is how 2 times thickness. So this becomes the effective that is B value. So D is this much. So D is this one is B. So this becomes actually 110. You can see that here. So 120 minus this radius into 2 times minus 2 into 2. That is 2 mm to this side, 2 mm to this side. So totally it becomes 110. So W becomes 110. T is 2 mm thickness. Therefore 110 divided by T is 55. So as per the code, this ratio is less than 68. So we have got 55 less than 68. If it is less than 68 and Fy is if Fy is 280, then you can take this P naught value equal to Fy as per the code. I have explained that in the earlier lecture. You can refer that. So P naught is 280 now. Now here to calculate that Zxt, what we have to do is we need to calculate the effective design width. The effective design width as per IS 801, which is there in page number 6 for stiffened elements. This is the equation. B by T is equal to 658 by root f into 1 minus 145 by W by T into root f. Here, please note that these values 145 to 268, 658, they are we have to take when f is in Newton per mm square. But whatever they have given in the code, when F is in kg per centimeter square, those values we have to take. For example, this is 2120 and this 145 is nothing but 465. You can see that. So this is the transformed equation if F is in Newton per mm square, because that is the SI unit. Now if you substitute those values, here B is the effective width or the design effective design width, T is the thickness. This ratio you are going to get as 51. So therefore B is 51 times T, 51 into 2, that is 102 millimeter. So 102 millimeter is the effective width of that flange portion. So overall width is 120. So in that we have to take the effective width as 102 mm. Since it is symmetrical about one of the axis, of course it is symmetrical about y axis. You can see this section whatever is given is symmetrical about y axis, but it is not symmetrical about x axis. That means your centroid will not be coinciding with the geometrical center. Now let us locate the neutral axis of the gross section as well as the reduced section. So neutral axis of the gross section, so it actually neutral axis passes through the center of gravity or the CG. If you locate the CG or the centroid of this section, then through that point neutral axis passes. So I will take this distance of this G from the top fiber as y bar, and using the concept of centroid, you can calculate that y bar distance by splitting this into, this is one rectangle, this is one rectangle, and this two webs as two rectangles, and this lip portion as the third part of rectangle. So if you use this formula sigma ai by sigma ai, you are going to get that y bar distance as per in mechanics you have studied that. So you are going to get this y bar value as 32.7 mm. So that means the centroid lies at a distance of 32.5 mm for the cross section. Now similarly you can locate the centroid with respect to the centroid of that reduced or effective section. So you can see here, in the case of reduced section, the effective design width of the flange becomes 102, which is splitted here now. You can observe here that this is 3 mm we are going to leave for that radius, and this 51, 102 is divided by 2 is 51 and 51. So this 8 mm whatever you get here, this becomes the ineffective portion. So this portion is ineffective, only this portion is ineffective from this gross section. So only rest of the things is effective. You can see that the total is 110, that the amount is 110, so only 102 mm. So that much is effective now. So remaining all portions are effective here. Web portion is effective and lip portion is also completely effective. Now, if on similar lines, if you locate the CG, or you can say it has some GR and this is G. So G is the centroid of this gross section, GR is the centroid of the reduced or the effective section. So if you proceed on the same lines and if you locate the centroid of this reduced or effective section using same formula, you can just see here. So here it becomes this sigma ai means the moment of the area of those individual rectangles with respect to the axis of reference. So if you refer on the same lines, if you do, you are going to get YR bar as 33.72 mm. So this distance, between these two, the eccentricity between the distance between the centroid of the gross area and the effective area is E. So E is nothing but YR bar minus Y bar. So this is that means it is 33.72 minus 32.7, it is something 1.02. 1.02 mm is the distance, that is the eccentricity between the centroid, distance between the centroid of the gross section and the effective section. Now this we need because we need to compute another thing called moment of inertia, because section modulus we can get by only after calculating the moment of inertia of the reduced section. So that moment of inertia divided by the distance of the farthest fiber gives the section modulus that you have learnt in your pure bending instance of materials. So similar procedure is used here. So moment of inertia we have to calculate now for this reduced or effective section by using parallaxis theorem. So I hope all of you know about parallaxis theorem. Now according to that, what I have done here is I have taken this rectangle separately for the flange, and these two rectangles for the webs I have taken separately. These two lip portion rectangles I have taken separately, and I have applied parallaxis theorem. So this first part is for the flange. So as per the parallaxis theorem, it is width into depth cube by 12. So width is 106 now. So 106 into 2 cube is the thickness, depth becomes the thickness, divided by 12. So here plus area of that flange 106 into 2 into distance of this distance from GR to the centroid of these two rectangles, or you can merge it as a one rectangle. This distance between the centroid of this and this, that becomes 33.72 minus 1 mm, because this is 2 mm. So this centroid will be at the midpoint, midline. So therefore minus 1 square of that. So this is parallaxis theorem. BD cube by 12 plus A into Y1 square. That we can say. So Y1 is the distance between the centroid of that effective section and the centroid of this flange portion. Similarly, for the web portion, there are two webs here. That is why 2 into that we take. So width of the web is 2, depth is 90. So 2 into 90 cube by 12, BD cube by 12 plus area 2 into 90 into distance between the centroid GR and the centroid of this one. So that distance becomes now, this distance is 45 because total is 90 minus this 33.72 square of that. Next, coming to the lip portion, there are two lips here, so 2 times, 2 into, so BD cube by 12, 13 into 2 cube by 12, so because this is 2, you can see that all the thickness of all the elements is 2 only, plus area 13 into 2 into this total distance from here to here is 89, total is 90, 90 minus 1, so it becomes 89, from here to here it is 89 minus 33.72 square of it. Now these are the moment of inertia of the three portions separately, and we had to add them to get the total moment of inertia of that reduced or effective section. So with respect to this XR axis, so IXR now becomes, after simplifying this, you are going to get 695,594.5 millimeter power 4. Now once you get IXR, when you divide it by the farthest fiber, so here I have taken the tension. So this top one is subjected to compression because it is simply supported beam. So top fibers above the neutral axis subjected to compression, bottom fibers are subjected to tension. So you can take any one side of the neutral axis. I will take the tension side. On the tension side, this distance YT becomes total 90. 90 minus 33.72, it becomes 56.28, that is YT. So when you divide this I by YT, you are going to get the value of ZXR. So ZXR is the effective section modulus of that section with respect to x-axis. So after this ZXR, we need to compute the value of M. So M is calculated, that is the maximum moment carrying capacity of that particular section, whatever is given. So we have to multiply that ZXR by FT to get the value of M. So M means MR, we can say moment of resistance is equal to ZXR into FT. So here ZXR we got 12359.5. 12359.5 into FT value, we have to take 168 MPa. So this is in Newton per mm square, whereas this is in millimeter cube. When you multiply these two, you will be getting the answer in Newton millimeter. Let us see what is the value. 12359.5 multiplied by 168, which comes out to be 2076396. 2076396. Okay. So this is in Newton millimeter. If you convert this into kilonewton meter, of course we are going to get 2.076 into 10 power 6 Newton millimeter or kilonewton meter. Now here, once you get this MR value, next step we have to equate this MR value to the maximum bending moment, which is WL square by 8 in the case of a simply supported beam with UDL. So now W is unknown now. So W is equal to 8 into MR divided by L square. Please note that everything is in Newton and millimeters. So we have to substitute in Newton and millimeters only. So 8 into MR is 2076396 divided by L square means it is 3000 square because we have to substitute in millimeters. Now we are going to get W in Newton per mm, so which is the same as kilonewton per meter. So this is the safe load carrying capacity of this particular section when it is used as a simply supported beam over a span of 3 meters. So now I will just calculate the value. 8 into 2076396 is equal to divided by 3000 square. So you are going to get the value as 1.845 or 1.85. You can take 1.85 or 8456 Newton per mm or kilonewton per meter. So this is the safe load the beam can carry. So you can observe here that whenever any cold formed steel section is given under bending problem, so first thing you need to compute the effective section dimensions. That is the effective width, and when that effective width is multiplied by the thickness, you are going to get the effective area. Then in the case of bending problem, we need to compute the effective section modulus. Very important. For that, you have to write down the effective section, and then you need to compute the location of the neutral axis of that effective or the reduced section. So from that, you have to calculate the moment of inertia of that particular effective section with respect to that axis of reference, and then divide that IXR by the any one of the stress values. Here I have taken tensile stress value 0.6 times the yield stress. So you are going to get the effective section modulus. Once you get the effective section modulus, multiply that by the effective stress. So effective stress we take 0.6 times Fy, and then after that you need to equate that moment of resistance to the maximum bending moment of that beam, and you find out the load carrying capacity W. So if it is concentrated load, you have to use WL by 4 here instead of WL square by 8. Here he has asked to save UDL, therefore WL square by 8 for simply supported beam. So respective formula we have to use that. The only thing is finally we are equating that moment of resistance with the maximum bending moment, and we are finding the unknown load.